chance of us doing it. And then the other aspect is with all our energy available coming from below the atmosphere, we have more extremes, more extreme weather, and we also have more extreme events in the ocean itself, which is heat waves, and many other consequences. So we care. On the left here is a graph from a recent paper, Cheng et al., that has a sort of composite of various estimates of the actual change in heat content. And this is mostly not modeling. This is their attempt to actually look at what actually is happening in the observations, augmenting this modeling. And do I have a point? Oh, yeah, excellent. And you'll see here various estimates. We've got Xana here, which I'll use again later. But you'll see that there's pretty much in the last few decades, what was considered to be kind of uncertain is very much now very certain that there is a significant change in the heat content of the oceans. So since the beginning of the modern era here, the last 60 years, we've had 400 zetajoules. That's 10 to the 25, I think it was, joules over the last 70 years. And that's a lot of energy. Unfortunately, when Xana published her paper, they tried to explain what a zetajoule is, and they started mentioning a nuclear bomb, and that ends up being the headline, which is something you shouldn't do. Don't try and make analogies which are exciting. So anyway, but there's 400 zetajoules in 70 years. It's a lot of energy. But it leads to, on an average, a small temperature change of 0.07 degrees. It feels like a small number. Turns out to not be a small number. This is one of the hard things about this signal. It actually feels like small numbers, but they're actually very, very big in reality. So that's heat uptake in the real world. And I'm here speaking as a climate modeler. And the reason I care about heat uptake is it makes my life very complicated when you're trying to build a climate model if there is a thing called heat uptake. So just as a starting point, if I'm trying to build a climate model, it's very, very convenient if you can build a climate model that if there was no pre-industrial force, if we're into the pre-industrial forcing where we think that humans haven't had a chance to change anything yet, it'd be very, very convenient if you say, oh, well, that was a steady state. So we would like very much to make the assumption that pre-industrial forcing was essentially an equilibrium state. And the reason I've just put this, it's not true things up here, is that there's a group of people in the office next door to me who get very upset when we make this assumption, and they're the glaciologists. So the glaciologists look at this time scale of order a few hundred years, and they say, well, that's just one time step. For them, it's very much a changing state over this time period. But for us, building the dynamical part of the system, the fluid dynamical part of the system, the oceans and the atmospheres, over these time scales, it's very, very convenient for us to say, let's try and bring the system into balance in equilibrium. So for a given state of the biosphere, let's try and make that assumption. And this work by Xana a few years ago, trying to estimate the history of heat content. So this is the same sort of plots we just saw in the first graph. You see that before, in the 19th century, it does look like it was pretty much nothing was happening. And so it's a reasonably good, when I say reasonably good, we can arguably reason that this is an okay assumption to make when we're trying to initialize a climate model. There wasn't anything happening at the beginning. So this is what we mean by pre-industrial controls. We will assert that there was an equilibrium that will start from. And we use this pre-industrial control as a baseline for comparing all of our projections. In principle, that pre-industrial control should be absolutely steady, equilibrium in a statistical sense. But in practice, no one generally can build steady models because we have errors. And so models always drift. And so we'll end up using that control to actually use as a baseline correction. So you take away drifts, for example. You always do this in any projection in CMIP. You'll see that they always have a high control, which they use to offset their actual projections. So on the right here, I'm showing some the evolution of global ocean temperatures as a volume average from two different models, circa 2005-6. So this is the CM 2.0, CM 2.1 models from GFDL. That's the famous lab in America. And this model was different only because of the atmosphere. In fact, it's the same ocean model underneath it. So this is just showing you the impact of a good atmosphere versus a model of an ocean atmosphere that had trouble with. But you'll see here, this is the 1864 control one we use the industrial control. And you'll see here in this model that these models, their ocean temperature is drifting. So this model over 1,000 years was drifting 0.4 degrees C. And I was telling you that 0.07 was a big number. So this is how good our climate models were in those days, right? And this is why we had to do these baseline controls in order to, when we do a projection, such as this model here, which is using the 1990 forcing, that model there, you take away the signal from here in order to get the best ideal projection there. So these are big changes in the ocean. As we said, the real observed change was 0.07, and we were modeling 0.4. This is just the global means. So let's just talk about the ocean for a little bit, because we are here interested in the ocean. And we asked the question, how does heat actually get into the ocean? So I'm not asking how does sunlight get into the ocean, because let's assume that there is sunlight has gone into the ocean. The question is, how does it actually get redistributed within the ocean? In the upper part of the ocean, there is a lot of energy available for moving that heat around. And when I say a lot of energy, I mean the energy available for doing mixing. So there's the winds, we've got buoyancy-driven turbulent processes. That stuff is working on timescales of hours to days. That's how you can deepen a deep convection site over the course of a few days. You can get water down to a kilometer depth. And that is a vertical transfer of, downward transfer of heat. So that's happening on short timescales. And it's primarily controlled from the surface, from the atmospheric forcing. But also there are internal ocean processes, obviously the turbulence and so on, but then there are also other processes try to come into balance. So those instabilities, we refer to them as sub-mesoscale instabilities. And in particular, the mixed layer itself can exhibit these instabilities that try to be stratified in the upper ocean. And those are happening on similar timescales, slightly longer than ours, but certainly over the course of weeks, as you find these instabilities trying to compensate for the buoyancy gradients being introduced from the forcing. But that's just the upper ocean, and it's very noisy and messy, and there's a lot of energy available coming from the atmosphere for doing all of that. But then in the interior, and that's the majority of the ocean, and by that I sort of mean primarily the thermocline and below there, we're now looking at an evolution on the timescales of years to millennia, and there are basically three main processes by which we need to think about, that are responsible for moving heat around. There's the large-scale circulation, right? That's the gyres, that's the wind-driven ACC. There's the mesoscale eddies, which is kind of all of the instabilities on the depth scale of the thermocline. And then there's mixing, and that's mostly in the form of driven by or provided, the energy is provided by breaking internal waves. Mostly. I mean, there is shear instabilities, there are other instabilities, but I think the lion's share of the mixing that happens in the interior is coming from the internal waves. So this is just a diagram I've taken from McKinnon's summary of her CPT on internal wave-driven mixing, but it's not a coincidence that we have projects in both Europe and in the US trying to look specifically at these kinds of processes because they matter for the global ocean and the energy balance of the system. So that's how the ocean works. And then when we actually build an ocean climate model, we can actually start looking at what the model is doing. So this is from a paper a decade ago by Griffiths, where he was describing what was then kind of a cutting-edge high-resolution model. It's a 10th of a degree climate model. And he was able to compare that, in that paper, he was also able to compare that to coastal resolution models. But this was an analysis of this 10th of a degree model, in which they were, essentially resolving the mesoscale eddies. And there's a lot of curves on here with awful colors. I shall ignore most of them. The ones I want to point out are, first of all, this dashed green one is the vertical heat flux associated with the mesoscale eddies, which is now able to resolve. So this vertical heat flux, and of course there's a problem with how you define eddy. So there's always an issue with how you define eddy, but we'll just take this as given for now. That it's okay. There is an upward transfer of heat by that process of transport by these eddies. And that green line is almost a mirror image of this red dashed line, which is the transport by the remainder of the flow, i.e. the mean flow. So this is the effect of the mean circulation, and that is a downward transport of heat. So is that a surprise to anyone? Why? So just as a quick sanity check, just think about the ACC, the wind-driven ACC. You've got a zonal wind driving an Ekman transport, which is equatorial, and that's going to pump, and let's assume that the ocean is positively stratified in temperature. That's going to pump warm water downward and bring up cold water, right? So just that channel alone, the dynamics of that channel alone, you can see that that is a downward heat transfer by that mean wind-driven circulation. And then at leading order, the Southern Ocean is pretty much everything from the point of view of APU. So the eddies. So the eddies is an interesting one. It's kind of the reverse. So the idea is eddies are trying to slump the available potential energy. So just as the wind was making available potential energy by pumping warm water down and bringing cold water up, eddies are trying to do the other opposite, trying to extract available potential energy, which requires them to slump, in effect, slump the ice field the other way, which is the same as carrying warm water up and cold water down. Okay? So the signs of these, you can kind of rationalize them, even though there's an issue of how to decompose flow into parts. But the sum of these two, red and green line, actually ends up becoming this black line. And so there's a very strong compensation. The actual transport, effective transport of heat in the ocean is the residual of two large terms. So in the interior, so this is a plot of the top 1600 meters. If we just look at the lower half of this, in the interior, there is only one other term that can be significant for the balance of the black line, and that would be the pink line, which is the vertical diffusion. It's labeled the vertical diffusion, but that's the diabatic terms. Okay, that's the vertical. Now, the diffusion, diabatic terms are mostly written as diffusions. Diffusion is always down gradient, right? Stratified ocean, warm over cold. Down gradient means a downward heat flux, right? So diffusion is unequivocally always downward. And so what we expect, if there was an equilibrium, is for the transport processes and the diffusion processes to be in balance. Diffusion is unequivocally downward, but in fact, we are finding that the advection is also downward in this model, even though we expect it to be upward if it was going to be in equilibrium. And this is just a direct measurement of why the model was not in equilibrium. And was it the Phoenix graph? Yeah, here it was. Oh no, it wasn't. It was the latest graph, sorry. And so in fact, this model is not in equilibrium, it's taking up heat. This because the black line and pink line are not the signs in the balance of each other. So this is kind of what I'm going to be talking about. We need to build a climate model, and in order to do my pre-industrial initialization, for example, or to do to model anthropogenic uptake, we need to do our best job at parameterizing the diabatic processes because they are the principal term left over, but have to balance our best attempt at resolving the circulation, and by that, by the time we're done, we're going to be resolving eddies. And in order for those to be in good balance, we have to minimize the thing which I've been spending most of my career trying to deal with, which is to minimize the spurious mixing, which is a part which is not explicit in our models. So I want to just start talking about how the ocean responds. And this is going to be turning the problem around a bit. This is some work by Bob Hallberg. He's now got a student working on this. And I'm going to turn the problem around. Rather than saying, how does the ocean take up heat? What we're going to do is ask, how does the climate model respond to changing the diabatic process in the ocean? So this is an experiment where the model started from an equilibrium state where there was this blue line here, where there was a prescribed diffusivity. The model was equilibrated. And as you can see, it very much was in equilibration for 2,000 years, right? So basically, the ocean temperature was not changing. And then what he does is he increases the background diffusivity in increments of 10 to the minus 5 meters squared per second. So that's kind of a canonical small diffusion radiation. Okay. And then what happens when he does that? He does it instantaneously. He does it in these various experiments. And you'll see that in each of these experiments, what happens is you've increased the diffusion, which means you've increased the downward heat uptake in that model, which means the ocean is going to warm. And that's what happens. The mean temperature of the ocean increases steadily, monotonically. And it's almost linear, it's almost a linear response with the diffusivity added. So you can warm the ocean up by around half a degree per 1 times 10 to the minus 5 of mixing with wet. One thing to note here is the equilibration is on the order of thousands of years. Okay, so this is one of the reasons that this problem is hard, because it's expensive to equilibrate the model. Running in a climate model of thousands of years is essentially the cost of it. That one experiment is basically the cost of seeing it for any one institution, because that's how many years you would run to do some of the projections. In 10 experiments, that's 10 experiments in 100 years. So this is the experiment set up before, and then this is what it actually looks like in the ocean interior. So basically, you've increased the diffusion, you're taking out heat, and what you see is that you get the warming signature. This is the change in temperature we're looking at. You see a warming signature primarily in thermocline, because that's where the strongest gradients are, right? So everywhere we're seeing a downward flux of heat, but it's the convergence where the curvature in temperature, which is in the thermocline, is giving you this convergence, stronger convergence of heat here, so you're warming in the thermocline. This is after 150 years, and eventually the signal propagates down, diffuses down, and you see it after 2,000 years equilibrium. The entire ocean has warmed. So here's a quiz for you. So this is the global temperature I'm showing you. Sorry, this is the zonal average section. I think actually just specific, but that was the global average. So remember that everywhere, all these experiments, the whole globe is warming in terms of the average. Can someone tell me what SST looks like? Remember, we've changed the diffusion, we're taking up heat. What happens to the SSTs? In equilibrium, I'll give you a clue. In equilibrium, everywhere is warmer. We just saw the zonal average, right? It will change. Okay, it will change. How will it change? Okay. Does everyone expect it to be warmer? That's the trick. Okay. This is the weirdest thing. The SSTs in this climate model do something very, very unintuitive until you get used to thinking about it. Remember, we are uniformly warming up the global average temperatures, uniformly increasing, right? In the first 10 years, the surface cools. And it's just to think about, to get comfortable why that is, think about what sets a sign of the heat flux or maybe the perturbation heat flux in a climate model. You need to have a downward heat flux across the surface in order to support that increased downward flux within the ocean. And the only way you can do that is to have a preference for putting more heat in, which means you need to have a colder surface. So that's one way of thinking about it. That's not a causality, that's like a consistency. But in the first 10 years, unequivocally the ocean cools. And just as a side comment, a lot of us learned the hard way that when you're building climate models, you're looking to look at the response to some perturbation. You often see the opposite of what you expect to see. For example, you might see an AMOC drop or the ACC plummet or something like that. Even though in the long term you really expect it to be both sides. And this is an example of what's going on here. You get a cooling. But then over the next 60 years, that cooling swaps around. You start to see higher warming, and then eventually in equilibrium, everything is essentially warmer, because it has to be, because the whole ocean is warmer. So that's just a little lesson about how unintuitive climate models are. Okay? So remember that the global average was constantly increasing, but initially you see it's cooling, then it also over a few decades that disappeared.
Yes, the heat flux must be positive, right? The change in is positive.
Exactly.
It's easier.
No, at that point it stays equilibrium. So this is one of the few models where we've actually been able to afford to run it to equilibrium because it's an affordable model. But yeah, this one actually does equilibrate to that. It's interesting, isn't it?
Positive heat flux.
Because This is relative. Sorry, this is relative to the initial relative initial conditions. So yes, it has to be. This is all anomalous. We talk about anomalous relative to the baseline condition. Okay, so that's just aside the issue about how complicated the response to climate models is. But the lesson was that there was a signature, and this signature here, I forgot to mention it. Whenever we're building and looking at the bias in our climate models, this is a very common signature. We recognize this almost instantly in any model we run. The first thing that happens is we get this bias. And so that's one way of thinking of that is, well, it means that all of our models are too diffusive. And that is not necessarily an untrue statement. That's just a lesson here. And I think that's something that will pan out. And that's true even of our current models. So I'm going to now talk about a more recent model from the one that we were just looking at. And this is some work we did about 8 years ago. And this is looking at where some of this mixing comes from. But it's not looking at it from a process level. This is looking at it from the bulk perspective. So what I'm going to show you here is something we've been able to do uniquely with our new model, Model 6, which is able to use any vertical coordinate. And the spurious mixing that we're going to talk about a bit more later is associated with using Eulerian vertical coordinates. And we'll talk about that later, explain why that is later. But first of all, I just want to show you the evidence. So what I'm showing you here is our eddy-permitting model in blue, which is of a quarter degree. And so it's only permitting values, it's not resolving them. But we'll say that it's eddying. And this blue line here is using a hybrid, in fact, all of these models except the dash blue, all these models are using a hybrid vertical coordinate where it's trying to be a isopycnol in the interior, and it's only at the surface where we have these active mixing processes that we switch to a z coordinate. So the majority of the ocean is isopycnol. At least if that's the intent. And so this model here, we've managed to build a model that is, over the course of 300 years, essentially in equilibrium. This is actually a force ratio model, so it's a bit easier, not a full-time model. And so we managed to build a model that's mostly in equilibrium. And then we also have another model we built, which is the orange line, which is a half degree, and so therefore not eddying. It turns out there's this kind of step change between a half degree and a quarter, where a half degree, at least our model, doesn't eddy, and so we have to parameterize the eddies. And so in this orange line, we added a Jenner-Williams parameterization and got it into balance also. But now that lets us do two things. One is, in our eddying model, we can switch from this hybrid isopycnol approach to a straight up Z model. Okay? So that blue solid line to that blue dashed line alone is just a change in vertical coordinate. No physics changes, no nothing else, just the vertical coordinate. And you'll see that it shoots off at 0.8 degrees per 300 years. That turns out to be around the same as what the earlier models in the first slide I showed you, CM2.0 and CM2.1 models. That is comparable rates. That's actually slightly less than those models. But that explains one reason that those models had to be warming up so much, and that why it's so hard to build climate models that didn't warm up. Because if you're using a coordinate that does not preserve water properties, then it simply has to have this, well, it unfortunately has this implicit spurious mixing. So that's one message here. And the other part is that if we take the coarser resolution model and turn off the eddy parameterization, it also warms up. So this is consistent with what I explained earlier, that eddies are an upward flux of heat. Take them away, you've effectively got a downward flux of heat, and that's why this model here is warming up. And that's almost similar sort of magnitude. So that just goes to show that spurious mixing is in the same ballpark in terms of size or amplitude as some processes we really care about. For reference, I've just put in here Zanner's estimate of the actual observed ocean contact. And you see that the errors due to either the coordinates or lack of doing the eddies properly are basically on par or larger than the signal we're looking for. So this is the situation we're in. They also have on here something we'll talk about next, which is if we increase the resolution of the model from a 4th degree to an 8th degree, in principle, the resolving circulation is better. And indeed, it looks like the eddies are now more efficient. And in fact, this model is cooling off, meaning we have failed to balance that model as well. So this is just a story about how big and important getting counterwise getting the eddies right is, and also getting the spurious mixture reduced. So that said, we actually have a newer series of models, which we call the CM4X series, which is Steve Murphy's led. And we've got papers submitted now, and we're waiting for them to come out. And the CM4X model is basically a revisit to the physics. So we've retuned the physics, the parameterizations. Every time you publish a model, you discover only after you publish it there are numerous bugs and numerous mistakes and parameterizations and so on. So we've fixed a lot of those, and then we've also increased the resolution from a quarter to an eighth of a degree. And the first thing to point out on this graph is this is an industrial forcing, fully coupled model now. So this is a climate model. And the first thing to point out is that this blue line, which is the eighth of a degree reaching model, is able to equilibrate and stay flat in only a century. So remember, the first curve I was showing you was the equilibration time of ocean models is millennia. And this model seems to be responding within a century and equilibrating. So that's an interesting result. We don't know if this is going to be true for all models. It could just be that we got lucky. And I'm afraid to say that that's often very much part of the game, is being lucky. But this is still an interesting result that we finally have a model where we do not have to actually run it for 1,000 years to get to a steady state, an equilibrium state that we can then start doing that climate science with. So that's interesting. And then, just as before, if we reduce the resolution to a quarter degree, indeed, the motion warms up again, presumably because we're not resolving the eddies quite well. And for reference, that's the CN4 model, which is, so we can move over that. So this is the model I showed on the last slide. This is that change. And the black line is the 10th degree model that we analyzed early on when we looked at where these vertical flux profiles is. So you see that systematically, we've gone from the era of, thousands of zetajoules per century to zero for the baseline, which is, I think, quite an achievement. I'm sorry. Well, unfortunately, sometimes it is bugs, but no. Most of this was actually, I think, one of the most important ones between 4.0 and 4x was actually. We looked at our bottom boundary layer parameterization. We realized we were doing way too much work. So we basically had 100 times more work being done in the mixing at the bottom. And so the bottom boundary layer is one of the primary sources of heat uptake. This is the bottom of the ocean if it mattered for the heat uptake, right? Just think about that. But then we also had improvements in the tuning of the ocean boundary layer, the mix layer. We call it GFDL with our mix layer parameterization. And then what else do we have? Oh yes, we also changed the numerical methods we used for the vertical remapping, which we'll come back to. In fact, we'll that later. So that model is we're very excited because it.
The version before, the 4.0 was also with the
yeah, so sorry, I didn't make it clear. So 4.0 is the new model of MOM6. And before that, all of the models before MOM6 and CN 4.0, those models were using the Z coordinate in MOM5. And so MOMs 1 through 5 essentially were the traditional Z coordinate equations. Yeah, I didn't make that clear, sorry. So just a quick reminder though, I mean, we've been talking about this metric, this global metric, which we managed to get to zero tendency. So, you have excitement about that. But this is the error we still have, right? So when you average over things, often you have pluses and minuses and you get to zero. But in fact, we still have a lot of errors. But nevertheless, it's still an amazingly good model. This field here is the eighth degree on the right. And you'll see that we still have what looks like the same patterns of error as we have on the left. This is SST I'm showing you. But these numbers in the top left are actually the critical ones. We've got a mean error and an RMS error, and they are both smaller than the one on the left at a quarter degree. And these numbers have been systematically decreasing for each generation of model. This is how we improve models. But it's very, very hard to fix these large-scale structures a lot of them are actually associated with the atmosphere. And this is one of the things you have to live with as an ocean modeler. If you want to make a better ocean model, become a meteorologist. I mean, that's a serious statement. I mean, it's the surface forcing is the thing you have to get right if you actually want to improve the ocean. We're at that point. Okay, but I'm still going to focus on improving the ocean model. So I've given you a story about how we can build a better climate model, and now we've talked about some of the things we did to get there on the numerical side in particular. So first of all, I just want to make sure we agree on what the origins of spurious mixing are. So I've got some schematics here to just make it clear what goes wrong when we evaluate a format and why I think the format is actually a good framework to be working in. And I have to speed up. I have 110 slides. So this schematic is just showing you three isospectral layers with a flow that this white line arrow is just a flow along the isospectral. So let's imagine the circulation on a gyre with tilted isospectral, and you've got a steady flow in that gyre along the isospectrals and no diabatic processes. To represent that transport along those layers and on a fixed grid, you have to have transport going across the grid lines, both horizontal and vertical, to realize that diagonal flow. Okay? That's just the way it is. With an oleum grid, the oleum grid will not line up with our signals or the direction of flow. And so you have to have these kind of diagonal structures. And whenever we have transport, there is always a numerical error. That's the next thing we have to say. So those two pieces of information together mean that there will be some sort of spurious aspect to the result, the numerical result, when I'm solving this problem in the Euler framework. In an isospectral coordinate model, the grid now follows the isospectrals. And so in that framework, the flow is now horizontal. So there is no diagonal component representing that nice steady flow along the isospectrals because it's simply a transport along itself. Now, sure, there's still a numerical flux and there is an error associated with that numerical transport, but it's now in isospectral coordinates, meaning the error is along the isospectrals. There's no diabatic component to that numerical error. Okay, that's basically the essence of why these models are able to reduce this spurious mix. There's another diagram here which is about another part of this, which is internal waves. So internal waves are transient phenomena where we just carry things which pass through your local frame of interest, region of interest, and generally, when they're not breaking, don't do anything. They're supposed to just move you upward in a nice, in downward, upward and downward, right? If they break, sure. Okay. Yeah, so I'm just showing you the schematic here with that three-layer system where I've got mode one wave, I've got convergence and then vertical motion here, and this wave will propagate to the right. Well, this layer in the middle, I've deliberately drawn with no flow. So because it's the node of it's the node of the mode as well. And the point here is that there is a vertical motion as this wave goes by, right? Now in Z coordinates, that vertical motion would just be up, down, up, down, up, down, and you would have that numerical mixing with that. But the interesting thing in the isospectral model is Lagrangian. So there's still the wave is still there is still motion, but in the isospectral coordinate there is nothing to do. There's nothing to be done other than move the isospectral. Your grid moves. It carries everything with it. There were no fluxes. There were no errors. So with an internal wave passing by, an adiabatic internal wave passing by, you can model it actually perfectly in terms of the diabatic because you don't get any spurious diabatic terms. So that aspect of the vertical grid is what led us to building 1.6. And so this is a schematic of our algorithm, and it actually reflects all algorithms we use in it's like a superset of all the algorithms we use in ocean modeling, both the Z coordinate models and the new hybrid model. You've probably heard of the term arbitrary Lagrangian or Lagrangian. This is the term that Wayne Black introduced in 2002 with HICOM. Some applied mathematicians prefer to call it the Lagrangian remap method. Details we could, in fact, I would love to get into these details, but maybe after lunch because I've got to run out of time today. But the algorithm is actually quite straightforward. It takes a state on a grid, And if you evolve that state adiabatically, they require you to move things around. And I'm talking about the vertical coordinate here, just the vertical coordinate. You have this branching phase where the waves, for example, will distort that grid. You have convergence, divergence, and it lifts things locally, it punishes things locally. But this is the same, this state is simply this with horizontal motion accounting for a movement of the grid. Okay? So this is the branching phase. Now, in a z-coordinate model, obviously the grid has been distorted. We want it to look like this. And so what we do is we say, okay, what's the grid? So we're just going to overlay a grid. We're just going to say, what should the grid be? So these black lines here are the grid we want, with the states that are under the branching state under the layer underneath it. And then we have to map the state on the current grid to the grid we want. So there's this remap phase. So the colors here are still solid within the layers. Okay. And over here, they are now solid within each Z cell. Okay? So the state from here to here is simply the remapping from the distorted grid back to the grid you want. Do you see that there's nice smooth colors along the layers here, and here they're now not smooth along the layers, they're discretized, right? So that's the remapping step. So that remapping step, if you take these three together, that is exactly the same thing you get as the W times temperature term in a z-coordinate model. It turns out to be numerically the same thing. This is just vertical advection in z-coordinates. For this particular scenario, my grid is a z-coordinate. And this is something that John Pukovich talks about, the analogy between what we're doing in z-coordinate models and what we actually can do in the more general sense. If I didn't choose z-grid here, if I had said, I want my grid, my solid lines here, to actually follow these dashed lines, i.e. I want them to say as isopycnals, then my gridding step would say, okay, I don't have to do my grid anymore. So when I do my remapping, nothing happens. So my choice of how I generate the grid at this step here determines what everything looks like. The grid, if I chose an isopycnal grid, after this step here, it would look exactly like this. So the grid generation, the choice of grid, i.e. the choice of vertical coordinate, how you define it, is everything. This algorithm can handle the limit of a purely Eulerian grid or the purely Lagrangian grid. And to prove it, we've actually done, although it's completely useless, but it's just to prove a point, you can truly have a random grid at this step. You can say, just make up random numbers that add up to the same column depth and remap to it, and that this model would actually work. It's a stupid model, but it's just to make a point that the grid generation is completely arbitrary. You as a user, as a scientist, are free to decide whatever you want. Now, as oceanographers, we would argue that we want to have a grid that follows isopycnals. So that's what we did in MOM 6 and 4. And I will jump forward to that result here. So this is how we do it. We have this is a description of Reinobel's hybrid coordinates. So we have isopycnals in the interior, and we're always trying to maintain those isopycnals in the interior. But we also have the problem that at the surface, we have unstratified regions due to mixing. And so isopycnals basically don't exist. And so in that region, we have to overlay a z-grid. So what we do is we say there's going to be a nominal z-grid, and then the isopycnals, if they crop against that depth, they send that big flat. Okay? So that's just it. There are two grids. There's kind of a nominal z-grid. We're trying to be isopycnal, and if the isopycnals outcrop too far, too shallow, we end up clipping them at depth. And it ends up looking like this. This is a figure from Alan Woolcraft. And so you see here, the isopycnals in here. This is a north-south section, north over here, south, Pacific. And here's the equator, and you see the volume of the isopycnals in the interior. And at the surface, you see that when they get too shallow, the isopycnals end up turning into Z layers. And so this is what our model looks like, the kind of model we produced for CM4. And it's kind of what we're currently using CM4X is like that. So it's quite straightforward and nightmare to analyze. So all our analysis is now done on Z-grids. So this coordinate I'm showing here is what we call the HICOM 1 in honor of the fact that it's Reinobel's idea. And it's our implementation of it. We made a few choices on it, and we made a lot of mistakes. And so when we say what did we improve since CM4.0, one of them was an absolutely stunning, stupid mistake on my part. We were in a rush to produce CM4.0, And we had this problem that we were using potential densities references 2,000 decibars as our isopycnal coordinate. And that turns out to be appropriate for most of the world, especially the North Atlantic. If you use anything shallower than that, we get an inversion of AABW in North Atlantic deep water. It's a famous result that if you use sigma 0, for example, those water masses are inverted. So we needed that to be a monotonic coordinate, so we use sigma 2. The layered isopycnal people have done that for a long time, so we did that. However, in the polar regions where you have a halocline, you get an inversion due to the compressibility if you use sigma 2. And so we said, okay, well, let's just undo that a little bit. So what we did was we said, we're going to use a density that's not referenced to 2,000 decibars. Instead, we will add in a small fraction of the compressibility, just a tiny little bit. And we actually use 1%, UCM40. So what we have done is we've taken sigma 2, where we added just 1% of the compressibility. So if you're at 1,000 meters, you have a reference pressure that is 1,900. Okay, so not so bad. So this was a last minute decision, and we were very excited because the model stopped blowing up. We ran the model, we produced CM4 results. And then Alan Woolcraft was looking at this one day about a year ago, and he pointed out that we have introduced dialectic motion into our system because density that is not referenced to a fixed reference pressure is no longer the margin. So by adding 1% of the compressibility back, I've effectively turned the model back into a 1% Z-coordinate model. There's a diagram here explaining, well, maybe I'll try and work through it. Basically, remember the water parcel to be displaced. It should be displaced along this dashed blue line if it was in terms of if it was referenced to 2,000 decibars. But what's happened is that we actually have changed the compressibility by moving it. And so we end up changing the density that it apparently has in our coordinate system. And it ends up, so we end up interpolating for a different depth. Instead of going for blue, we end up interpolating for this orange line. What that means is that we have a temporary displacement from, say, an internal wave. And the first thing we do is we start moving it, okay, across coordinate. That's where we get our spurious dialectic mixing from, because we ended up adding some flexibility. So that was a major mistake. In our next generation of models, we are trying to fix this, because that was really, it was such a forehead slapping moment. Alan said, did you know you've added compressibility, you've added Z-coordinates back into your model? I was like, one of those moments where it's like, oh dear, 8 years of work. So what we're going to do now is, in fact, instead of using sigma 2 for everything, we've now got a reference pressure for each interface. And so each interface now can have a different reference pressure. And that simply solves the problem that we can now tune that reference pressure to be more appropriate for the depths of that the isopycnal was found at. Now, it turns out to be hard because if you look at some isopycnals, some isopycnals that reach down as far as 4,000 meters actually do reach to the surface. So choosing a reference pressure that can span this density, this depth range is still hard. And so we're also now considering adding a slow variation of latitude to try and deal with this. But here's the inversion I was talking about. So this blue line is the density in sigma 2, in reference to 2,000 decibars. And this inversion of density here is due to the strong halocline. And if you just change the reference density, the reference pressure to just 1,000 meters, you can almost cancel that out and come back if you use 500 meters of strong activity. So tuning that reference pressure is going to be pretty important. But as I said, the North Atlantic is very, very sensitive to using the right entry density. I'm going to skip over some more numerics. I've been going too slowly. I want to just say there is, I said earlier, the user or the scientist can choose the coordinate, any coordinate they like. Random numbers is one limit. There's a nice piece of work that Angus Gibson, who was a student of Andy Cobb in Australia, has been doing. He's been with us for a while. And this is an interesting idea. It builds on some ideas from Hans Bouchard and Hofmeister about adaptive coordinates. So the algorithm can support any coordinate. So you're free to choose to build any algorithm to choose that coordinate. So this is an idea inspired by this group here that we're doing some one with. And what we're doing here is we're going to say we're going to move the coordinate with the intent of minimizing the gradients of potential density along the corner. So if you think about what that does, if all these other terms are gone, I've got terms of smoothing and installing and adjustments and so on. But if you just think about this first term here, that density adaptivity, if that is been acting for a long time and minimized, in principle, it means that the curvature of density along that circuit, along that coordinate, is minimized, and so it should look very much like a nice figure. So this is what we expected to happen. This is actually what happened. It was a very interesting result, and it turned out to be very useful. Even though we expected it to, approach ice signals, it ended up being very flat. And my first result was, oh no, it's another compressibility for head slapping moment. But it turns out that in fact what's happening here is locally, it's following nice signals. But on larger scales, that second order operator takes a long time, probably more than we know, to follow. So what it's doing, we initialized at Z. Locally, it's following the fluid, it's trying to be the Lagrangian, and then it's finding a little bit of adjustment needed to keep it along nice signals. And so we've got these waves and adjustments going on, which are where it's following the flow, it's keeping the fluid isosignal locally, it's just not doing it on large scale. And this is actually a huge advantage, because it means that we can actually maintain resolution. One of the worst and most annoying problems for us in isosignal world is that isosignals don't exist everywhere. So we have a lot of wasted resolution in our model. So this is a new coordinate idea. We're waiting for there's a paper being worked on right now. And we think this actually, they have this working in a prototype global model called Access 3, and we're hoping to try this out in our time model soon. So we haven't yet measured it. Angus Gibson has a paper where he measured this in a different coordinate system, so we will do that. We have we'll hold our judgment about whether it's reduced it enough. But there will always be some when you're not isosignal. So this is not strictly isosignal, but it looks like it's capturing somebody else. We'll find out in time. But it's just an idea. I want to just wrap up with a quick comment about the future. And it's a comment about the rush ahead towards using AI. And we're all doing it. I know that some people are doing some machine learning here, but the modelers, of course, are building emulators of their models, which is what we've been doing here. So I'll talk about that. But the punchline is, I feel like we might be rushing ahead and not paying attention to the lesson we've learned, at least I've just tried to explain to you, about trying to preserve water properties and do things in a conservative and accurate manner. So what we've done here, this is work that's sponsored by Schmidt Sciences and the project called N-squared lines, led by Lausanne. And we had a master's student, Surya Deshis, who built a emulator of the OM4 model I showed you earlier. And so he took that model and has managed to produce a network that is able to produce a basic state and temporal evolution of that state, which is actually really, really good. Here's some climatologies, and here's some time series. And these models, one of the first challenges you have with these emulators is building a model that's stable. So, it's what they call long rollout. So you build a model that can get you from day 0 to day 5 in one step. But if you then do it again and again, the early results for all these emulators, they would just blow up. So this is actually a huge result that we've actually been able to build a model that's stable. So that was a win. But one of the consequences of that is that the model is too stable. So this model is trained on the contemporary period of the JRA forced era, 60 years of data. And then we actually took that model and we changed the surface boundary conditions from 0 to 42.5 and 1 watt. And this is the response. So it's a good sign that the model responded. But this amplitude of that response is way too small. This model is too stable. Okay. So this is the first lesson we have about AI when it comes to heat uptake. Because we chose a model that simply maps a state from one time step to the next time step, and it doesn't pay attention to any properties such as conservation. So when it doesn't conserve, what it's doing is predicting a state based on the previous state without any knowledge about, fluxes adding up and that sort of thing. So this is a classic challenge for AI, which is how do you actually build in some constraints and physics into the systems? And so there's we're now working on some newer generations of that theory model, and it turns out that the simplest approach is, to me as a modeler, it's a prompt to use a fixer where you take a state and you just correct it, right? And as a modeler, I feel like, well, hang on, that's cheating. It turns out it's not really, because it's exactly the same thing as what I suggested on the right. But the idea of a fixer is you have your model that's predicting the state. And then you say, well, that state, the mean state wasn't being predicted very well, but I know that it should add up to the average of the fluxes. So you can just correct it, right? For a fixer. The meteorologists do this all the time in their GCMs, okay? As an ocean modeler, because I care about conservation, and preserving water masses, we would never do this, right? Second, we would never do it. We don't, I promise you, we do not do it, but the meteorologists do. So, but the thing is, that's interesting, is that if I was to write this model in flux form, so instead of producing the state, imagine I predicted the flux between levels, and then I could write it in flux form. Then this model unequivocally conserved because it's in flux form, right? But it turns out that the correction you end up doing is essentially the same thing. We've built in that the budget has to close. And that's all we're doing over here. So it's not actually such an impossible thing to consider, just correcting it after the fact, because your model is just an approximation of everything that's going on. So the fixes are something we're trying now, and we're also going to start trying to see if we can learn a model in this form. The approach that does not work is modifying the loss function. So I don't know if you're aware, in machine learning, it's all about optimizing, minimizing the loss function, where you have a network that's trying to model some data, and you can add as many terms to the loss function as you like. So in this case, I've just said, I want the model over here to predict to have a mean that is equivalent to the flux, right? Because the model is predicting the next state. I think I've missed the term here. But anyway, my point is that you can modify the loss terms and you can minimize that. The reason it doesn't work is this term is never zero, and so therefore this term is never zero. It's just a way of allowing the model to be wrong. It's slightly better, but it's never going to be exact. So you can't get that budget to close with that approach. Last minute, I will quickly rush through a general question. So I've spent most of my time talking about spurious mixing and trying to get the ocean models to actually model the heat uptake well. And in the emulator world, I'm struggling to understand whether we will get the right answer directly. So I was going to quickly explain what we did, what you do in an emulator. So you have a state that might be the real world, evolving on very short time scales, second to second, or a model that's doing a good job preserving properties in a density space with our time steps. And we're going from time step n all the way to time step n+1 with all this small subcycling, resolving dynamics. And then what you do is you say, I'm going to observe that state, and I'm going to build a training data set that goes from this state to this state. So I'm simply sampling my model for the real world at this long time interval. So this might be, say, 5 days, which is what we did. I'm putting a Z here because that's actually what we did. And this is what we're going to do in observations and generally any approach. You want to put everything into a nice uniform grid for convenience. And so you're going to map from your data space or your observation space into a Z coordinate. And then what you do is you train a model that goes from here to here with a nice long time step, which is why they're so cheap and efficient in my time Robson. Right? So you can successfully train a model that predicts here from here. That's what we did. The point is that this is in Z space now. So I've effectively built an emulator which looks like a general coordinate model in Z coordinates. Right? But the question I have is the data set, in principle, was obtained from a system that was perfect. Observations or 1.6 was perfect model. Is the emulator that we're training going to ever learn that inside that data set was an evolution of an adiabatic system that is better represented in a different space? I raise that question because it might be that we should not be working in Z coordinates if we're trying to build emulators. it seems hard to me that if you take a grid data product in Z coordinates, that it will ever have enough data that it could magically learn that this is going on behind the scenes. It's possible. So the machine learning people like to talk about latent space representation. They like to talk about it will learn eventually. There are universal approximators, is the expression they use. It must eventually learn with enough data that it's better for it to figure out how to remap back and do everything in this space and then get it here. That's in principle what should happen. But I think it will take an awful lot of data. And so if we want our emulators to actually learn from our history in motion modeling, we should perhaps not make the mistake of working in Z coordinates at all at the beginning. Right, so I'm done. Literally 1 minute over, so I apologize for running late. I start by saying that we have built a better climate model by paying attention to processes, but in particular spurious mixing. We seem to have built a model that remarkably can equilibrate very, very fast, which is probably luck, but also partly due to the improvements we've been making. Spurious mixing is definitely a real thing. We've learned, I think, that if you really want to do the Newtonian problem well, where you need to preserve water mass properties, and for example, worry about heat uptake, you do need to do this, pay attention to this. And I'm currently concerned that our rush to build emulators and be the first people to publish in Nature, oh, here's an emulator that can do a centennial simulation in 1 minute, that sort of thing, is probably not going to be much use to us in climate for the time being, because there is no way that they're paying attention to the right things for us. They're going to be very, very useful, by the way. I don't want to suggest they're not going to be useful. It'll be very useful for projections, uncertainty quantification. I mean, having something that can produce results just like that, very, very powerful. But climate problem, maybe we'll have some work to do. So that's everything I want to say. I'm sorry it's a bit all over the place, but thank you very much.